Hi there. Thanks again for joining us. This is Space Nuts, a Q&A edition. My name is Andrew Dunkley, your host. Terrific to have your company. Questions that we will be answering on today's program include the big crunch, gravitational waves, shifting magnetic poles, the use of the term dust. Somebody's got maybe an issue with that. And questions about the gas and ice giants and why do we think they've got rocky cores. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us for what will be the last time in a little while, because Fred's coming back next week, Jonti Horner, Professor of Astrophysics at the University of Southern Queensland. Hi, Jonti.
Good afternoon. How are you going?
Pretty good. And you?
Not too bad, dealing with the usual kind of too much work, not enough fun. Looking forward to a trip to a conference next week. I'm down to the Australian Space Research Conference, which is always my favourite meeting of the year. So it's perfect timing for Fred to return because I wouldn't have been easily available next week anyway. Hand over and everybody listening can breathe a huge sigh of relief because normality has been restored.
Oh, no, it's not like that. In fact, that's where we can start because we do have some comments from the audience. This came from Sam in British Columbia. He says, I just wanted to say how helpful I found the answer to the Lagrange points in mass question and how much I enjoy Jonti Horner's explanations, musings and answers. I know sometimes they seem a little more detailed than chatty, but I really enjoy that extra detail and context. I found the spatial contours explanation extremely useful. Thank you. So you've got a bit of a fan there. And another comment that I came across on our podcast group Facebook page, I appreciated all the attention Andrew and Jonti devoted to the government shutdown. My family suffered personally. That came from Martin, although there was someone else who didn't appreciate us going down the political line, but because of the impact it had on NASA particularly, it was probably something that was worth discussing. Yeah,
I think it is important. I understand that people don't like it when you get into politics too much and to your political views, but I think in this case it's something where colleagues of mine were being directly affected. I know people who had more than 4 weeks without pay, and we're here to talk about what's happening with space and exploration and research. And when there's something that's impeding that, it's important to discuss it. And it's doubly important, I think, when people are trying to use it for political capital to perpetuate lies about alien spacecraft.
Yeah.
You need to set the record straight to correct other people straying into politics when they shouldn't do. So, I appreciate the comments. I love the positive feedback. I try and not get too political in terms of my own views on stuff, but there are some topics which we do need to cross. And, my heart does go out to those who were directly impacted by the shutdown for whatever the reasons the shutdown was happening. It's not good when you have to go more than a month without food, particularly for those families who have two people who are both government employees and have children with mouths to feed.
Yeah, and we're talking thousands upon thousands of people, so it wasn't just a handful. Let's move on to our first set of questions. Bo in Melbourne has sent us two questions via our audio stream. Let's see what he wants to find out.
Hello, Andrew and Professor Jonti Horner. It's Bo here. Yes, your second favorite BO from Melbourne, Australia. I have a question for you. But first, I would like to do a fact check, please. A couple of episodes ago, Professor Watson talked about the Ganab-Gib, or the Big Crunch. And basically, he said at the end of the Ganab-Gib, matter will come closer to one another as the effect of gravity takes over. And we'll end up in a one giant singularity and collapse. What he didn't say was the effect of that on light. Now, my understanding is that obviously as stars and galaxies come closer together, the sky will get brighter and brighter. And as matter starts to fuse, will give out more heat and more light as well. So essentially, we'll end up in a reverse Big Bang, and then we will all come to a big blinding end. Both matter and light coming together in a reverse Big Bang. So I just wanted to see if that is correct regarding light. I'd love to hear Jonti's view on that. Now, my question is related to gravitational waves. We know that gravitational waves distort the fabric of space-time in a wave pattern. We also know that multiple gravitational waves exist because there are, black hole collisions and black hole and neutron star collisions happening throughout the universe. Now, what happens when those two gravitational waves meet each other? Particularly, what would happen to, the interference patterns as the waves starts overlapping each other at the peaks and the troughs? Do we see any changes to space-time itself? Do we see, for example, time speed up, slow down, or stop? Do we see gravity cease or increase or decrease? Just wanted to know what would happen to space-time and at that interference patterns, the peaks to troughs. Love to hear Professor Jonti Horner's view on that. Thank you very much, and please keep up your good work.
Thank you, Bo. Great questions. We'll probably start with the big crunch and the effect on light. Now, I suppose we have to consider the timing of events because the universe is still expanding, although now they're starting to think that acceleration is no longer speeding up, it's slowing down, or that the expansion. But it's still expanding as far as we're aware at this point in time. Fred has told us in the past that it will expand to the point where everything will move so far apart that we will just be by ourselves in the universe in blackness. So the question is that still going to happen? And even if it does, and there is a big crunch, what's going to happen to all the light anyway? So it's a really fascinating area.
It is, and it's really complicated. It's dealing with things that are incredibly far in the distant future.
Like it is next week or the week after, I think.
Absolutely. Well, with the way that time seems to pass quicker and quicker as I get older, it does probably mean that it will be next week. But it's a difficult one. So there is still some debate over whether the universe will continue to expand forever or whether it will turn around and begin to collapse. Reminds me of the Arthur C. Clarke quote about life elsewhere, which I'm going to botch and paraphrase in this case, which is that two possibilities exist and both are equally terrifying. Either, we expand forever or we don't, and they're equally scary in many ways. But assuming that we did collapse back down to a point, now that will likely happen at the point when all the stars have died, when everything has come to an end. And so you'll probably have a universe full of non-luminous stuff and black holes, and that's about it. Maybe so far away in the future that even the biggest black holes have evaporated from Hawking radiation. But whatever will happen, whatever is left will be squashed into an ever smaller place. That will include all of the radiation that's going through the universe. Now, we see the cosmic microwave background and we see it at very long wavelengths, at microwave wavelengths with an approximate temperature of like 2.9 Kelvin or something like that. I can't remember the exact number. That's because that light is redshifted because the universe has expanded and stretched that energy out. If the universe collapsed back in, you'd be going the opposite. You'd be blue shifting all the radiation. So as you squash the universe into an ever smaller space, because of the quirk of the fact that there is nothing outside the universe is both infinite and finite at the same time. So you can't be outside the universe because that's meaningless. All of the light and all of the energy in the universe will remain in the universe as the universe gets smaller. So my understanding is that as you get towards a hypothetical big crunch, the temperature, the pressure, and the density will just increase and increase and increase. And the universe will end in a very, very hot mess, effectively. So it will be like running the Big Bang backwards. Yeah. There'll be differences. We don't fully understand what will happen and how it will all go. We don't know whether that would trigger another Big Bang because, to be honest, we don't know enough about that time of the universe, and certainly I'm nowhere near the forefront of research in that to give a more educated opinion. But I know that the closer you get to the Big Bang looking back, the harder it is to be exactly sure what happened because the less information we have, and the harder you're having to push our understanding of physics to the point it breaks down. And the same will be true going the other way. You're just reaching temperatures and pressures that make no sense. You have periods when different forces will combine into a single force. I do not know with my level of knowledge whether the expectation is that those transitions would happen at the same point going back as they did coming forward. So I think that the exact details of how the big crunch would go are still very much up for debate if it were to happen. But I think it's very fair to say that it would be very bright, very hot, very unpleasant, and we wouldn't be around to enjoy it.
No, definitely. Well, yeah, it's like the restaurant at the end of the universe in Hitchhikers, you know. If we're not going to sit there and enjoy a wonderful dinner while it all happens around us, it's, I'd say humanity would be long gone by then, or transition into something else. I don't know. But I certainly don't think it would be like rewinding a film and watching it all just happen in reverse. There'll be some cataclysmic effect for sure. The main question Bo wanted answered was about gravitational waves, and they're out there, they're happening, we're detecting them all the time. But what happens when they cross each other? What's the effect? I would equate it to throwing two pebbles in a pond and the waves just cross over and that'd be it.
Yeah, I've done a bit of reading around on this one because honestly, I haven't got the foggiest coming into this. So my default assumption is that the waves would interfere in the same way that electromagnetic waves interfere, in that they'd add together. So you get a peak and a trough would cancel out, a peak and a peak would lead to constructive interference. So you'd get bigger and smaller instantaneous amplitudes. But you get an interference pattern. Reading around online, it seems that is broadly the consensus. So long as you are a long way away from a strong gravitational field, so you're a long way away from the source of these things, or you're a long way away from something like a black hole. And apparently the physics of the general relativistic treatment of this gets incredibly gnarly when you get to those kind of situations and nobody's really sure what would happen. The maths gets difficult. And the point is you're pushing the boundaries of what we know and what we can observe into the unknown. So what you have to do is you have to develop possible answers and test them. Build theories, make predictions, see what happens. But I think in general, if, for example, one of our big gravitational wave detectors, two waves came in at once, you would probably at that instantaneous location, you get an extra large peak or an extra large trough, or they'd cancel out. But because you might have more than one detector around the Earth, thanks to the directions of motion, you'd only have that specific type of interference at that specific detector. So it will probably give us a signal that if you've got multiple gravitational wave detectors around the globe, would be distinct and identifiable and would allow you to test that interference, if that makes sense. Now, my understanding of the typical gravitational wave events that we see is that you've got these waves that are building up from in-spiraling neutron stars or black holes, or a neutron star and a black hole about to collide, where you get very low frequency, very low amplitude waves that build to a sharp crescendo, which is why you get these attempts to sonify the data where you get this rising whistle, rising in pitch and rising in volume. So the idea is that you get a lot of small waves first and then you get a really big build to a crescendo and then fall off. So typically you probably wouldn't observe this happening with our current technology unless you have the incredible good fortune to have two events where you get the peak arriving at the same time, and that'd be the interesting test. So yeah, to summarize, I don't think anybody fully knows because you're pushing the bounds of what is known, but it seems to be that the consensus is that in open space, away from really significant masses or away from the sources of the waves, they would just have normal kind of constructive and destructive interference as the peaks and troughs go across each other.
Okie dokie. There you are. Thank you, Bo. Great question. Let's take a break from the show so I can tell you about our sponsor, NordVPN. With NordVPN, you can explore the web securely and privately no matter where you are, whether you're streaming space documentaries, downloading data from the International Space Station, legally of course, or just browsing from a coffee shop. NordVPN has your back. Fast connection speeds, no data logs, and protection across all your devices, including your smart TV, plus access to content from around the globe. It's like having a wormhole to the internet. Sorry about that. Without the black holes. Haha. Right now, Space Nuts listeners get an exclusive deal. nordvpn.com/spacenuts. Huge savings, plus an extra 4 months free. That is fabulous. nordvpn.com/spacenuts helps you stay protected online and gives you everyday access without any fear that your private data will be stolen. That's nordvpn.com/spacenuts. And don't forget to use the code word spacenuts at the checkout. nordvpn.com/spacenuts.
0G, and I feel fine.
Space Nuts.
Our next question comes from Paddy. Reflecting on the discussion around the shifting of the magnetic poles, if they were to flip, how would the field behave as it transitioned the equator? Would it spin with the Earth's rotation? Would it let in more debris, solar radiation, and or cosmic particles? And to go full Hollywood disaster movie, given the visual representation of the magnetic field suggests an apple shape, could the funnel of the magnetic field become like a magnifying glass scorching the Earth as it crosses the equator? Love the show. Keep up the great work. That's from Paddy. He's put a bit of thought into this, and I love the sci-fi component. But is this in your ballpark, this kind of thing, as an astrophysicist?
It's closer to my ballpark than the Gnabnibs and the dark energy stuff. I mean, I'm still not, I would argue, an expert, but I'm closer to it, and I have done a bit of reading. Now, what I would say here is actually the Wikipedia page for geomagnetic reversal is a really interesting read. It's very in-depth and contains a lot of good historical information. So while I acknowledge Wikipedia is very much secondary rather than primary resource, I think for topics like this and topics in astronomy, the articles tend to stay fairly on task and fairly accurate because people will fix them if they break very quickly. And that reading that should, to some degree, immediately put Paddy's mind at rest in terms of the Earth getting baked or scorched or Hollywood disaster movie type things happening at the time of a field reversal. Because we've had at least 183 reversals in the last 83 million years, which means that these things have happened regularly through the period of the Earth being inhabited and have not caused any mass extinctions. There have been some suggestions that periods where you get the magnetic field locked in one direction for very long periods of time, which last happened during the Cretaceous period, where you had something like a 50 million year period where the magnetic field didn't flip. There have been some suggestions that when those very long periods of time come to an end, that it could trigger a certain amount of added volcanic activity and stuff like this, and that may lead to some traumas for life, but never quite at the level of a mass extinction. And there's a couple of beautiful figures plotting out the flips that have happened going back about 180 million years, talking about these periods where the magnetic field gets locked into a single orientation, nothing much happens for a long time, which is known as a superchron, and then you get other times when you get more flips in a short period than typical. There's one here. 51 reversals occurred during a 12 million period, centered on, I think it's 15 million years ago. So you get periods where there's a lot more of them happening. You also get periods where it tries to flip and then goes back to how it was. So the idea that you had from school that the Earth's magnetic field is essentially we have a giant bar magnet in the middle of the Earth and it's very controlled and static, as we said on the podcast a few weeks ago, that has fallen by the wayside. Now, the magnetic field being generated by wibbly-wobbliness and convection currents and all sorts in the Earth's outer core through a dynamo effect is fairly well understood. And these field reversals are something that falls out naturally in modelling. So people have not had to hugely increase the capacity of their modelling ability when modelling the behaviour of the outer core to make them happen. They happen naturally from the way the models are set up, which is really interesting. What seems to happen is that unlike the sun, where you get the magnetic field reversals at about the time when the sun's magnetic field gets the strongest, and that's all down to the tangling up of the magnetic field lines as the sun rotates as a fluid body, not a solid body. On the Earth, the magnetic field reversals tend to occur at times of low magnetic field. So what tends to happen is that the dynamo becomes less effective, things become confused in the inner core. You can even get periods where you get multiple north and south poles while the magnetic field in the dynamo breaks down and reasserts itself, and then it flips over. There is some discussion over how quick this can happen, with most studies seem to suggest it can take anything from 2,000 to 12,000 years, but sometimes it could be quicker, sometimes it could be slower. It's all complex, and it's because it's all tied to this turbulent roiling of the liquid metal in the outer core. What this means is that Firstly, if you shift where the north and south magnetic poles of the Earth are, they will rotate with the Earth. That's, in fact, what we see with pulsars. Why we get the pulsars is that the magnetic fields and the rotation axis are not lined up. So you get a magnetic hotspot on the surface of the pulsar where you get the magnetic pole is, where any material around will be funneled down the magnetic field to hit there. You get this hotspot. You get lots of radiation emitted from the poles. And as the pulsar rotates, those poles sweep like lighthouse beams, and we get pulses of radio waves when that beam sweeps across us. So it's fairly well understood that the magnetic field rotates with the Earth, and therefore, if the magnetic pole was in Kenya or somewhere like that, it was somewhere near the equator, it would be rotating with the Earth. That's kind of how it would work. And that would probably happen if the flip was the North Pole wandering to the Earth's South Pole. In reality, though, it seems that these reversals are more almost like the Earth's magnetic fields weaken, they become disestablished, you get all this confusion, and then a new field establishes itself, which I think is probably part of the reason that the flips are even less periodic than you'd think. They're talked about as being totally random, but I suspect that's added to by the fact that if you wipe out the Earth's magnetic field and turn it on again, if you imagine you had a 50-50 chance of it being north-south and a 50-50 chance of it being south-north, then only half of the time it weakened would you get it flipped to the other polarity. And so that might be part of what's going on there. So it's all really, really complex. What would happen is that we would get, to some degree, a greater flux of radiation hitting the top of the Earth's atmosphere, the charged particles that get diverted around us by the magnetic field. It will get less effective. But it's worth noting that our atmosphere is incredibly effective protection for us anyway. I saw one article saying our atmosphere is as effective at protecting against the solar wind and charged particles as a 3-meter layer of concrete would be. So the atmosphere does a very, very good job, which is why it seems that these magnetic field weakenings don't lead to mass extinctions and things. They will have a bit of an effect on the upper atmosphere. Stuff will happen. There are suggestions that maybe you could get a little bit of additional atmospheric stripping happening during these times from solar radiation, but effectively the impact would not be that great on the surface of the Earth. It would probably play merry havoc with scouts who are doing orienteering and people doing their Duke of Edinburgh Award and things like this, where you follow a map and you've got to use a map and a compass, because if the North Pole is in a different place every year and weaker, that's going to be a pain for navigation. There would doubtless be significant effects on technology. Obviously, and we saw last week with a really good solar storm and aurora again, that we are to some degree at the mercy of big solar storms. We discussed in the past the likelihood of events like the Carrington event being a problem for satellites and for unshielded electronics on the surface of the Earth. And if the Earth's magnetic field were weaker or were in the process of reversing, then an equal strength solar storm would do more damage because less of it would be deflected. But you wouldn't end up with the kind of giant lens baking strips along the Earth. Fortunately or unfortunately, depending on your point of view and your love of Hollywood dramatics, that should be fine. It would be an interesting event. There are people who keep suggesting that this kind of thing is imminent. The problem there is imminent in geological timescales doesn't mean imminent on a human timescale. So the last reversal, I believe, was about 780,000 years ago. The average timing of them seems to be out every 500,000 years, so people say we're overdue. That skips the fact that actually the timings are very random. It's a bit like waiting for a bus. I use this analogy all the time. You know, if you've got a bus due every 5 minutes, you may wait half an hour and 5 come along at once. You did not know. And with these kind of reversals, that's exacerbated by the fact that we tend to get long blocks and short blocks. So I'm looking just at the last 5 million years. And if you go from 5 million years ago, black on this plot is the polarity we have now and white is the other one. 5.01 million years ago, it flipped so that south was at the top. Then 4.89 million years ago, we had, 80,000 years of our current polarity. Then it flipped back and we had 17,000 years. Then it flipped back for 17,000 years, back for 18,000 years, back for 8,000 years. And then there was a 600,000 year gap. And so it's very, very spotty. The last flip was 780,000 years ago. Before that, it was only a 12,000 year gap. And then there was a very long period between 1.06 and 1.78 million years ago when it was the opposite polarity, except for a single measurement at 1.19 million years ago when it was the other way around. So that was a very short flip. So, in all honesty, saying that we're overdue for it is a bit like bumping into somebody grumpy at the bus stop because the bus is 30 seconds late. In all honesty, you've got no clue when that bus is going to arrive. And looking at the time periods in the Cretaceous, there's 2 or 3 of these mega long breaks, these supercrons that have been identified. 2 are very confident, one's a bit more controversial. But the most recent one in the Cretaceous was more than 50 million years with a single polarity. And that's the equivalent of being at the bus stop, but the buses are on strike.
Yes, yes. Wouldn't be a problem in Japan. They are very strict about their timing. In fact, I remember a story a couple of years ago about a train driver who lost his job for being 2 minutes late.
Yeah.
So
I remember that in Switzerland. One of the bizarre experiences when I first moved to Switzerland for my first postdoc, kind of 22 years ago, was being on the train platform and the train was slightly late. And people were checking their watches and correcting their watches because they thought that their watch was wrong rather than the train being late.
wow.
And it's like, I'm used to British trains where if they come on the correct week, you're lucky, you know.
Yes, the Australia's a bit like that. Yeah. Although they're pretty good most of the time. You only ever hear about them when the press has decided to stick the knife in. But
absolutely.
Yeah, 9 times out of 10, they'll be okay.
At least most places have trains. I don't know if I've told this story before, but my understanding of the reason that we don't have a fast train from Toowoomba to Brisbane is that there used to be a train service, and in the 1950s, the family that ran the coach service on the roads from Toowoomba to Brisbane got elected to the Toowoomba Council and shut down the railway because it was competitor. And so 70 years later, we still have no fast rail to Brisbane, and it comes up every few years that we should have it, and it's just never got going again.
Yeah, I'm sure there's a lot of that going on. Yep. But great question, Paddy, and it sort of throws a curveball into, if it happens, if there is a magnetic pole flip, does that mean we are no longer down under but up over?
Absolutely. Or pop over.
Yes. That could be the case. Oh, gosh. No, we don't want to cause any trouble. Let's just leave things as they are. Thanks, Paddy. This is Space Nuts with Andrew Dunkley and Jonti Horner.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our next question comes from Howard Bennett. Howard is in Penang in Malaysia. I have a question about the term dust. D-U-S-T, dust. The word is used indiscriminately throughout astrophysics with no real definition. I don't know. I know it's not the same as the dust bunnies under my bed, but what exactly is the space dust that obscures our heart of galaxies and inhabits the empty space between galaxies? Not to mention moon dust and deadly dust storms on Mars. Most confusing. Maybe we need a new word.
Yeah.
So when we refer to dust in space, what are we talking about, and is it all the same stuff?
It's all sorts of stuff, basically, but the commonality is that it's small pieces of solid material. So that's effectively what you're talking about. It becomes confusing occasionally in the solar system, for example, when we draw the line between meteoroids, which are particles of effectively dust going around the sun, and asteroids, which are bigger things going around the sun. And typically people place a division there at about a meter diameter. So the same object that's 1.1 meters across you'd call a small asteroid, at 0.9 meters would be a meteoroid. And that's just because we have to have a boundary somewhere. And materials that are considered dust in space will include things that at home you'd consider ice. If it's solid, it's dust. And the hotter it is, the less things can be solid. When it comes to the stuff on the moon, then you're talking about the dust being surface rocks that have been pulverized by impacts. So you have these tiny particles of lunar regoliths, which are small pieces of dust because they're small pieces of solid material. Lunar dust is pretty brutal because there's no moisture and no weathering there. So it's incredibly sharp-edged and abrasive. And that's why it's such a problem for future astronauts. It's why it's a problem technologically. It's why when they came back, they had to clean the astronauts.
Vacuum them, I think they did. I remember Buzz Aldrin described walking on the moon as walking on talcum powder.
Yeah.
Very, very slippery.
Lots of very fine dust particles, with the exception that talcum powder is a lot less abrasive. I think a better analogy, although it's not perfect, to the kind of things you get that cause miner's lung and things like that, where you've got particles of dust being created by explosions or digging underground that haven't had time to be rounded off by moisture and weathering yet, and they cause huge problems for people who inhale them. I believe that was a part of the problem with asbestos when you inhale it. Actually, it's to do with the sharpness of the particles and the damage that they do. So that's the kind of moon dust stuff. Similarly, when we talk about dust storms on Mars, the dusts there are those particles of solid material that are small enough that they can be lofted into the atmosphere through a variety of processes, not just the wind, but there are solar radiation processes that can levitate dust off the surface of Mars, including one that is really fascinating that I did some research on with colleagues, again, 20 years ago now, which is this weird weird light-based effect. We're familiar with kind of radiation pressure and the Ponting-Robertson effect. These are things we talk about a lot, but there's also something called photophoresis, which is to do with the absorption and re-emission of light from very small dust grains, that when you're at a very specific size range can exert a really intense force. So what happens is that when your dust grain absorbs some light, it temporarily has a temperature gradient on it. That temperature gradient depends on how big the dust grain is, whether the near side or the far side of the dust grain gets hot, because if the light penetrates most of the way through, the far side is a bit that absorbs it and gets hot. So you get a dust grain that's hotter on one side than another. If that dust is in an atmosphere that is not too dense and not too low density, the gas particles, from the point of view of the dust grain, will be perceived as single impactors, single billiard balls. And when they hit the dust grain, they stick briefly and then leave again. And if they hit the hot side, they'll leave with more energy than when they leave the cool side. Mm-hmm. So you get a force. Now, this is a really quirky force I'd never come across until I saw a talk from a couple of physicists who were talking about dust grains on Mars. And we looked into it in the form of what this would have as an effect for planet formation disks and stuff like this. But what's really quirky is that this is only effective over a relatively small range of gas pressures. If the gas is too thin, it doesn't happen. If the gas is too dense, that individual probabilistic single gas molecules adhering and leaving doesn't happen. But in those range of pressures, it can be up to 10 or 100 times stronger than all the other forces, and Mars's atmosphere, particularly in the highlands, is the right pressure, that this can actually levitate dust grains off the surface of Mars, and is viewed as potentially being helping to trigger those dust storms to start the dust getting kicked up into the atmosphere. So all sorts of really cool stuff there. The other thing that I found out from those physicists that we worked with way back then is that when you buy the little light windmills that you can get in an evacuated shell that are meant to show radiation pressure, they're actually not. They're using photophoresis because there is some atmosphere in that bubble still. And the Havells, one is coloured white, one is coloured black. The black side gets hotter, and you get this photophoresis force happening rather than radiation pressure, which is interesting and quirky. Coming back to the question, all the way to the question is, whenever astronomers use the term dust then, what they're meaning is particles of solid material that are too small to be considered asteroids or planets or things like this. That gets the catch-all of dust. And it behaves very much like dust in the Earth's atmosphere. Red light penetrates it more easily than yellow light, which penetrates more easily than blue light, because the longer the wavelength, the better you can pass through. Which is why if you look at photographs of some of the wonderful dark nebulae in the night sky, like the Coalsack Nebula, which is ahead of the Emu in the sky to the traditional owners of the land here in Australia, like many of the Barnard nebulas. Barnard did a big study of finding dark nebulae all across the sky. If you look at photographs of those that have been taken in full colour, and you zoom in around the peripheries of those clouds, you'll see that the stars right at the edge look red. And that's because you're seeing them through the outer edge of the dust cloud, and the blue and the yellow light is scattered away, the red light penetrates through. And you can see this very well if you look at some of the famous photos of the Coalsack Nebula. It's really, really distinct and noticeable. Yeah. And it's because dust is dust is dust. I appreciate it gets confusing because we use the term in so very many contexts as a throwaway thing. And to our experience on Earth, because it's warm here, you don't consider flakes of ice and snowflakes as dust. But if you
or smoke, you don't think about smoke as dust, but that's exactly what it is. Can you see that photo I took during the big bushfires a few years ago?
Yeah, what's spooky about that is that I've seen the sky diminished and denuded by bushfire smoke, and I've also seen it from dust storms, dust that's been kicked up and elevated off the surface of the Earth. And I would have never expected this, but When it's really, really bad, they both lead to a very red sky. But when it's not that intense, you can actually tell the difference because the sky looks different between lofted dust and smoke. You actually get a very different kind of reddening. And that's because the particles are different sizes. But if I took a bucket of smoke or a bucket of snowflakes into space and scattered them into the solar system, they'd just be considered dust.
Yeah.
Small pieces of solid material.
There you go. Howard, if you can think of a set of names to cover the various categories, let us know. But I think just using the term dust is probably the easiest way to deal with it by the sound of things. Thanks for your question. Hope all is well in Malaysia.
3, 2, 1.
Space nuts.
Our final question today comes from Martin.
Hello, Space Nuts. Martin Berman-Gorvine here, writer extraordinaire in many genres, with yet another question. How do we determine whether the gas giants and or the ice giants have rocky cores? And if they do not have rocky cores, what might they have inside? Possibly of tangential relevance, I saw an article that appeared earlier this year in SciTech Daily saying that analysis of Hubble data shows that methane has been depleted at Uranus's poles in recent decades, which begs the question, is Uranus outgassing methane? Oh, sorry. I shouldn't have said that. I don't know what came over me. I will do penance immediately. Berman-Gorvine, over and out.
Thanks, Martin. I did wonder where he was going with that. I shouldn't have been surprised. So, to gas and ice giants, if they don't have rocky cores, what do they have? I mean, there's been some suggestions that some of them just have a liquid center, like a nice, chocolate you get at Christmas. Could they all be different? I mean, did they all have to have the same kind of thing? It's not, we're not talking about dust here.
Well, there's a couple of different things that lead into this and should make the distinction between the planets we have in the solar system and objects elsewhere, because the only planets that we can get up close and personal to are the ones here at home.
Yeah.
The background here is that traditional views of planet formation involve a process called core accretion. So this is where you take the solid material, the dust, from the protoplanetary disk, and if you're out beyond the ice line, that dust includes a lot of icy material. Solid material agglomerates, forming bigger and bigger objects until eventually you get something massive enough to start gathering the gases and hold on to them. Because whether you keep hold of an atmosphere or not depends on your mass and the strength of your gravity. The more massive you are, the more gas you can hold on to, but also the more capable you'll be of capturing hydrogen and helium, which are the main gases in the universe. So the idea is that Jupiter and Saturn got to 10 or 12 Earth masses, which is kind of viewed as being the threshold for gathering up the hydrogen and helium gas, fairly quickly, hoovered up a lot of hydrogen and helium, and they became the gas giants. And that's why the name gas giants has been used. For Uranus and Neptune, they never really got big enough to gather hydrogen and helium before the hydrogen and helium had been blown away. But they gathered huge mantles of methane, ethane, ammonia, things that are typically ice at that kind of distance, and a gas phase, depending exactly how far away you are. And so you've got these objects that are significantly composed of material that could be considered ices, or gases that are more massive, so therefore have a higher escape velocity, and therefore are easier to hold on to with a lower mass. So the distinction between the ice giants and the gas giants is a compositional one, and it's to do with how they formed. They always used to just all be called gas giants. The ice giants idea came in with different models of planet formation, because what we tend to do with planet name classification, with things like whether Ceres is an asteroid or a dwarf planet or both, whether Pluto's a planet or a dwarf planet, what we tend to do is we tend to place boundaries as humans to allow us to group like with like and separate things that are functionally different in origin or have a different history. And we do this in our day-to-day lives. We have children and pensioners, we have adults, we have people who suddenly wake up one morning and they can drive a car when the day before they were legally not allowed to do so because they've crossed this magic threshold. It's a very human thing. The nature of them in terms of having cores is therefore initially an outcome of our best understanding of how these things could form. The idea is that you need to form a kernel of solid material to get enough mass in order to accrete the gas. Now, there's an alternate model which probably ties into the formation of objects in binary star systems, where when you've got a much more massive disk of material around a star, you can get an instantaneous gravitational instability where you get a very gas-heavy object formed very, very quickly that wouldn't need a core as a nucleus around which it forms. It would have solid material in it, but that solid material would just be at the level that the background material would have. So the composition of an object formed in this way from this gravitational instability would be the same as a bulk composition of the disk. The composition of an object that forms from core accretion would be richer in the solid material because they form a big amount of solids before they gather any gas. Once they're at the point of gathering the gas, they gather everything in the same amounts as are in the disk. So you end up with something that has a large amount of disk-like composition plus a chunk of solids added in. But the thing is, the bulk of those solids are down at the bottom, so you can't really measure that remotely. So how do you tell them apart? Well, to be honest, for things around other stars, we can't yet. So what we need to do instead is look at their orbits and the structures of the system and see how they fit with these different formation models. And this is, I think, going to, in the next few years, lead to a shift in how we define what a brown dwarf is, where historically a brown dwarf was something between 13 Jupiter masses and about 80 Jupiter masses, was something that was a failed star rather than a giant planet. But we're finding objects that blur that boundary more and more. And I think we'll probably shift to a different definition which looks at the formation mechanism and the presence of a core. So if you've got something twice the mass of Jupiter but formed through this gravitational instability method, that will be a very low mass brown dwarf. Whereas if you've got something 20 Jupiter masses that has a solid core, that will be a very massive planet because it formed through core accretion. I think that's probably where we're going. That means then that you can draw inferences on this based on the structure of the planetary system you've got, based on the orbits of the objects, because these different formation mechanisms would form very different systems. But here in the solar system, we actually can eventually figure out whether giant planets have got a solid core or not. In order to do that, we need spacecraft to be orbiting those planets for a lengthy period of time, preferably on highly elongated orbits like Juno. This was one of the key points of the Juno mission, where you've got a spacecraft going round on a highly elongated orbit, which is experiencing the gravitational pull from the planet. And when you're very close to the planet, your orbit is not just sensitive to the mass of the planet as if all of the mass was at a single point in the middle of the planet. You actually become sensitive to the distribution of mass within the planet. Fundamentally, a planet that has a lot of gas on top and a small dense core that has a varying density throughout will affect the spacecraft differently to how a planet that was uniform in density throughout would do. Now, to some degree, we do this on Earth where people map the density variations at a very local scale for GPS satellites and things like that. And you've seen beautiful gravitational maps of the Earth where it looks like a deformed potato, effectively.
Yes.
So same kind of idea with Jupiter and Saturn. By using the data from Juno, by using Cassini data from around Saturn, we have a fairly good idea that those planets do actually have cores of solid and liquid material deep within them that would have formed through this core accretion process. So that's why we can be fairly confident that they have rocky cores here, where rocky is basically meaning anything solid. There'll be iron and nickel. There'll be water ice, and there'll also be liquid metallic hydrogen and things like this. But there will be a solid kernel at the core from which those planets formed. There is some interest that comes from this because I think Jupiter's core, I think it was Jupiter's rather than Saturn's, the data has revealed is there. It's a bit more massive than expected, but also more spread out and slushy. And that is thought to be potentially evidence of a late giant impact on Jupiter, where there was a late addition of a big chunk of solid material, in much the same way that there was a giant impact that formed the Earth and the Moon, a giant impact that stripped the surface of Mercury away, leaving Mercury denuded. Giant impacts were a huge part of planet formation. But in order to be absolutely definitively sure that you have a solid core, you need those close-up spacecraft measurements to be able to distinguish the subtleties in the gravitational field that result from something that is not uniformly dense, but has a varying density and has a, I guess, significant internal structure. We can do that in the solar system. We haven't yet done that for Uranus and Neptune because we've never had orbiters go to those planets, and I look forward to the day that we manage that. But even if those missions start being planned now, they probably won't launch till the 2040s. I will be retired by the time they get there, but I'll still be watching on eagerly. For the planets round of the stars, we have to draw on the nature of the planetary system they move in the orbits and draw inferences then on which of the formation mechanisms that they had. And that's where the complexity about brown dwarf versus giant planet comes from as well. So it's a wonderfully deep and complex question. In terms of the methane on Uranus, I think that is not that Uranus is outgassing the methane, it's keeping the methane to itself, a bit like when I put the dogs in a locked room. They keep their methane to themselves, and it's sometimes not that pleasant when I go back in there. But rather the methane levels varying because of the time of year and the seasonality of weather on Uranus. I think that's probably what's happening there.
Okay. It's a great question. Martin always comes up with a ripper or two from time to time, and some good questions as well. And that was a good one. Thank you, Martin, and thanks for the joke. Loved it. And that's where we are going to finish up. And Jonti, thank you for filling in for the last 7 weeks or so while Fred took a vacay. We really do appreciate it, and we'll certainly have you back down the track. Thank you.
It's always a pleasure. And in the meantime, I'll keep my eye on the Facebook group and cheer on people sharing Nightwish videos. I saw that, and that made me happy.
Yeah. I knew someone would.
Yeah.
Fantastic. Thanks, Jonti. Thank you very much.
That's a pleasure. I'll catch you next time.
Okay. Bye-bye. Jonti Horner, Professor of Astrophysics at the University of Southern Queensland, filling in for Fred for the last several weeks, and we will get him back on in the not-too-distant future. And thanks to Hugh in the studio. Hugh couldn't be with us today because he's been having trouble sitting. And he went to the doctor, and the doctor said, "Oh, you've got a ring around your anus." Oh, I couldn't help it. Thanks, Martin. You inspired me. I'm done.
Been locked in a room with my dog.
Yes, indeed. All right, we're done. Thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.